Alright, so we're going to move on to Chapter 7, Section 5. And in this section, we're going to kind of put everything that we've learned together. We're going to use a lot of the identities. We're going to solve expressions by simplifying using the identities and so on. One concept that we're going to talk about real quickly is the concept of principal values. All the trigonometric functions are periodic. They repeat their values over and over again every time they cycle through a period. So when we solve expressions, we're going to find that they have infinitely many solutions to them. One thing that we can do is restrict the possible solutions to be within a set of values within a range, so that we're only considering a finite number of those solutions. The idea of principal values is restricting the values of sine, cosine, or tangent between two quadrants. We'll get a couple of examples of those when we go to example 1 and 2. So we're going to solve this expression, sine x cosine x minus 1/2 cosine x equals 0, for the principal values of x. And we want to express the solutions in degrees, so we'll follow each of those things. The fact that they ask for principal values means that we don't need to come up with an expression that would give us all possible solutions, of which there's infinitely many. So we're going to first only consider values between 0 and 360, and when we simplify this a bit more, we'll see which two adjacent quadrants between 0 and 360 that the solutions lie in. One thing that we can do when we're looking at problems like this is we want to get everything over to one side and factor. That's going to be one way that we can solve these expressions more easily. So here we have everything over to the left already, and we have this common term. So if we can spot a common term, the first thing we want to try is factoring that out and see if it gives us something that's easy to solve. So we have cosine x, and then what's left behind, sine x minus 1/2. The reason we're factoring is just like when we had polynomials that we factored. Once we get everything on one side, and everything on that side is all products, it becomes a lot easier to figure out when the function is equal to 0. Because this function is either equal to 0 when cosine x is 0, or it's equal to 0 when sine x minus 1/2 is equal to 0. So we can solve both of these independently. Just from basic knowledge of the unit circle, we know that cosine x is 0 at pi over 2, or they ask for degrees, so we'll put it in degrees. Cosine x is 0 at 90 degrees, and also 270 degrees. Now, sine of x, between 0 and 360, sine of x minus 1/2, we could rewrite this as sine x equals 1/2. And again, from knowledge from the unit circle, we can tell that sine of x is 1/2 at 30 degrees. And also, over on the other side, we've got 150 degrees. So these are all the answers between 0 and 360. But they wanted the principal values. Now, if we're taking cosine and sine, if we look back, the principal values for cosine are in quadrants 1 and 2, and the principal values for sine are in quadrants 1 and 4. So the only overlap here is quadrant 1. So we're just going to pick values that are in quadrant 1. So we'll say when x is equal to 90 degrees or 30 degrees. those would be our principal values. Obviously, there are other values that work, and really there's infinitely many, so we're just picking a couple. Okay, now in example 2, they don't ask us for principal values, but they do give us a limited range for the solutions we should provide. They want x to be between 0 and 2 pi. So again, there are going to be infinitely many solutions because sine and cosine are periodic and repeat their values over and over again. But the answers that we're going to provide should just be answers between 0 and 2 pi. Now, because they listed this as 0 to 2 pi, our answers are going to need to be in radians. So for this problem, the first thing we'll want to do is let's collect everything over to the left. So we'll have cosine squared x minus sine squared x minus cosine x plus 1 equals 0. Unfortunately, we're not able to factor in this case because we don't have a common term among everything. So we'll have to be a bit creative. There are a couple of different things that we could try. Just looking at this, we can see that this was one of our identities. But that was a double angle identity, and I'm not sure that that's going to make this any easier to solve because we still won't be able to factor anything out. We also have Pythagorean identities for cosine squared and sine squared that could help us convert from one to the other. So maybe we could use that to convert everything into cosine so that we have all common terms. So let's try that. So the identity I'm talking about is this: sine squared x plus cosine squared x equals 1. That's the Pythagorean identity. And we can remove sine squared x by solving this and saying sine squared x is equivalent to 1 minus cosine squared x. So we'll make that substitution, see if it makes it any better. Let's go ahead and simplify a bit. So we're going to have cosine squared x minus 1 plus cosine squared x minus cosine x plus 1 equals 0. So we've got some stuff that's going to cancel out here. This minus 1 and positive 1 are going to sum to 0. And we'll have 2 cosine squared x minus cosine x equals 0. So there we go. So now we have something that we can factor out a common term. So we'll pull out our cosine x, and we're left behind with 2 cosine x minus 1. And same thing, this is going to be equal to 0 when either of the two factors is 0. So we've got cosine x is equal to 0, or 2 cosine x minus 1 is equal to 0. And again, we want to give all the solutions between 0 and 2 pi. So cosine x is 0 at pi over 2, which is 90 degrees, and 270 degrees, which is 3 pi over 2. Over here we can solve this. Cosine x equals 1/2. That's on our unit circle. And that's going to, cosine x is going to be equal to 1/2 when x is 60 degrees. So that's pi over 3. And then it's also 1/2 when we're at negative 60 degrees. But since they wanted it between 0 and 2 pi, we'll just be 60 degrees shy of 2 pi. So that's going to be 5 pi over 3. And that's going to end up being our 4 answers. So we'll use all 4 of those as our answers, since those are the ones between 0 and 2 pi. You guys have some homework tonight, so just check the calendar. Make sure you do those problems.